Welcome! All right, let's talk about predicting the future. Today, we're going to move way beyond just simple guesses. We're going to dive into how modern forecasting uses these really powerful tools called state space models to understand and even navigate what's coming next with a whole lot more confidence. So, predicting the future. It's easy, right? Well, not so fast. I mean, if I asked you what sales are going to be next month, sure, you could throw a number out there. But what if you're wrong? By how much? The real game here isn't just about picking one number. It's about grappling with the uncertainty that surrounds that number. And this right here is the absolute key difference. On one hand, you've got a point forecast. That's a single guess, like sales will be exactly $5,000. It sounds confident, but let's be honest, it's almost guaranteed to be wrong. What's way more useful is on the other side, an interval forecast. This gives us a range, admitting that the future is a space of possibilities, not just one single point on a map. So yeah, the real challenge in forecasting isn't about gazing into a crystal ball to find one magic number. It's about accurately mapping out that whole landscape of what's possible. And this quote just nails it. Simple methods might give you that single number, but they leave you totally in the dark about the most important part. How confident should you be? For that, you need something much more powerful. You need a model. Okay, so let's really dig into this crucial distinction. What actually separates a simple method from a true forecasting model? It sounds academic, but it makes all the difference. Think of it like this. A method, like we've been saying, it just spits out that one number. It's simple, for sure, but it's an incomplete picture. A model, on the other hand, is trying to understand the why. It specifies the underlying structure of your data. It doesn't just give you a number, it gives you prediction intervals, that measure of uncertainty. It's just way more robust and informative. It's the key to doing serious forecasting. So let's pop the hood on the engine that powers these really sophisticated forecasts. Let's look at the state space model. So what the heck is it? Well, a state space model uses these things called state variables, which are unobservable, to describe a system. Just think of these states as the hidden forces, the invisible currents, like trends or seasonal patterns, that are actually driving the numbers you can see. And the whole thing basically boils down to two main parts. And here they are. First, you've got the observation equation. This is what connects the dots between what we can actually see and measure, our data, to that hidden underlying state. Then, second, you have the state equation, and this part describes how that hidden state itself evolves and changes over time. It's a system that's always learning and updating. Now, if that sounds a little abstract, don't worry. The absolute best way to get your head around this is with an analogy. Let's just imagine for a second that we're trying to track a submarine. Okay, so the submarine's true, exact position, that's the hidden state variable. We can't actually see it from up on the surface. But what we can see is the observation, that little ping that shows up on our sonar screen. A state space model uses that sonar ping, the observation, to estimate the sub's true location, the state, and then predict where it's headed next. But here's the thing. This is not a one-size-fits-all solution. There are lots of different flavors of these models. So how in the world do forecasters pick the right one for the job? They use something called an information criterion, or IC for short. You could just think of it as a score that helps find the Goldilocks model, the one that's not too simple, not too complex, but just right. It rewards a model for being accurate, but it also slaps it with a penalty if it gets too complicated. The goal is always to find the model with the lowest score. And you'll almost always see two main types of these scores, the archaic information criterion, or AIC, and the Bayesian information criterion, known as BIC. They just calculate that complexity penalty a little bit differently, but the rule is always the same. Lowest score wins. So let's see how this works in the real world. Here's some data on automobiles. A forecaster would line up all the different models and look for the one with the lowest AIC and BIC scores. Just scan down those two columns. Two numbers should pop right out at you, 0.39 and 0.48. See them? They both point to the exact same choice. The log additive model is our winner. It's that simple. Of course, real-world data is never perfect. It's messy, it's complicated. So what happens when you get these extreme, totally unexpected values that could throw your entire forecast way off track? We call these outliers. An outlier is basically just an extreme observation. And if you don't account for it, man, it can cause some serious errors, both in how your model understands the past and how it predicts the future. It's like a rogue wave just came and crashed into your dataset. And they tend to show up in a couple of common patterns. You've got an additive outlier, which is just a one-time shock. The data spikes or dips, and then it goes right back to its original path. But then you've got a level shift, and that's a whole different beast. That's a permanent change. After the shock, the data just keeps on going from a new, totally different level. So how do we actually spot these things in the wild? Well, we use a tool called a z-score. Honestly, you can just think of it as a weirdness score. It measures exactly how far away a single data point is from the rest of the herd. A really high z-score is basically a big statistical red flag waving at you, saying, hey, look at me, I am not like the others. And here is the proof that dealing with this stuff really matters. This is passenger data from Dulles Airport. Look what happens after we adjust for an outlier. You can see all the error scores go down. But here's the crucial part. Look at the holdout sample. That's data the model has never seen before. The errors go down there too. That tells us our model isn't just neater, it's genuinely better at predicting the future. Phew, we have covered a lot of ground. So let's try to distill all of this down into the key lessons for smarter forecasting. Okay, it really comes down to this. First, stop just guessing a single number. Use a formal model so you can understand the whole range of possibilities. Second, get your hands dirty. Examine your data for trends and seasons. Third, and this is so important, always test your model on data it's never seen before. That's your holdout sample. And finally, use diagnostic checks to make sure your model's assumptions are actually valid. So if there is only one thing you take away from all of this, let it be this. A great forecast is not a magic number. It's a map. It's a map that shows you the hidden patterns, the underlying structure, and, most importantly, the boundaries of the uncertainty that you're going to have to navigate. Which, it leaves us with one final thought to chew on. We have these incredibly powerful models, but at the end of the day, they are built on historical data and past patterns. So what kind of events, what kinds of shocks to the system can even the very best models never ever see coming? Something to think about. Thanks for joining me.